Let's get started with the second problem from the list that I'm going to tackle, and this is the linked list cycle. Simple problem. After we understand some of the basic algorithms that we used to have to solve cycles in general, especially in linked lists. Here we have given the head of a linked list, determine if the linked list has a cycle in it. If there is a cycle in a linked list, if there is some node in the list that can be reached again by continuously following the next pointer. Internally, pose is not used to denote the index of the node that tail's next pointer is connected to. Note that pose is not passed as a parameter, so we do not have pose. Return true if there is any cycle in the linked list, otherwise return false. Simpler than that, not many constraints, definitions, not many things to put in the board. Started to put things in the board. As we know, we use the board. Something that I've learned recently, how to use the board. You know what I'm saying? So we have the head, which is a linked list. Here in the first use case, we have head is 1. I won't use I'll use it like this. 3 is 3, 2, 3, 2, 0 and 4. So 3, 2, 0 and -4. So we have a constraint that declares possibly downstairs there, down in the text on the paper here, that the constraint can be negative. That says that this can be negative. So alright, cool. And the position is 1, so that means that the last node, when the cycle is detected, will point to node 1. How do we solve this? And what do I need to return? I just need to return true, right? So I know that I should use the Floyd's algorithm to solve this, which have an incredible video that someone posted and I studied before, so I don't think that's necessary for me to explain how Floyd algorithms actually work. But so guys, I decided to record this brief review of this video here, because that's where I've learned Floyd's algorithm from back in the day, and obviously I forgot how it works, right? And then now I'm just trying to recap here with you guys.
Right. So I'm going to be explaining more of the why, because in terms of how, you kind of saw it in the video. It's pretty self-explanatory. What you do is you have 2 pointers, right? The hare and also the tortoise. You have one here and one here, right? And then one of them goes 1 by 1, and then the other one goes 2 by 2, like this, right? And then once they meet, let's say they meet here. Once they meet, this is the point that they meet. I'll put it in blue. Then what you want to do is you want to put the pointer back here, one of them, and the other pointer back here, and then you just traverse 1 by 1 this time. So 1, 2, 3, 1, 2, 3. So once they travel at the same time, they will meet at the point where the cycle begins, right? So, but the question is, like, why does it work? Why does it guarantee that once you do this algorithm?
That will be enough at this point here, because all we need is to prove that both pointers will encounter once on the linked list cycle. We don't need to return or go all the way back and return the specific node where it starts or anything like that. All we need here is to say it's true or false. So that's where is the middle of the cycle here. Let's sketch let's catch up with the problem he mentioned here. That's where they meet. It's the meeting point. Where would be our meeting point here? At this specific cycle, we would have a hare, the tortoise, and we would. So if we start hare, we'll go 2. Then tortoise goes 1 on the first iteration. Then hare goes another 2, and then tortoise goes for another 1, and then hare goes to 1, 2, and then tortoise goes to another 1, and then hare goes to 1, 2, and then meet at -4. So that's the meeting point here in this case. What that means if I reset here, and now I navigate one by one both pointers, they will meet at the start of the cycle, and that means we have a cycle here. Okay, we get to the same problem that we get usually in any type of algorithm. How are we going to start iterating here? Well, we know that in linked list there's only one way that we can navigate, and is by using the next pointers. So if with the hare we would like to navigate 2 pointers, two moves by time, and then for the tortoise just one node by time. That's what we would like to have here. And for that to happen, I mean, like, if we have a cycle, we will always have a next dot next, right? But we first must guarantee that we have next. If that doesn't happen, it's false, right? So this is one of the basic things here that we would need to acknowledge when having cycles in linked lists. Is like next dot next will always exist if there's next. If there's a cycle. If there's no cycle, that will be false. Therefore, we could say that, for example, while hare dot next what would that mean? It would say hare and hare dot next. That means it will start the loop, and if the loop keeps going, we could say hare for hare dot next, because if it is a cycle, it will have a next dot next. And tortoise is equal tortoise dot next, right? That means they will be able to navigate here without any issues, and when hare is equal to tortoise, we return true, right? And then there's the edge case here, the exception, where it's else, return false. Why? Let me tell you why. Basically because if we don't have hare dot next or next dot next, that means it won't have a cycle. Really break the loop and get into the oh, we don't even need the else here. Yeah, we don't even need the else. It's not an exception. It's like, if you're in the loop, you will fall into here and it will return at some point when have a cycle, and if you don't have a cycle, it's because you don't have a cycle. You know what I'm saying? And then you'll catch basically the second statement here outside the loop. Let's catch up with the code here and try to code this solution that we've got into there. Hare and next and hare dot next. Um, while we have those guys here, obviously I think we would need to define our pointers here. Hair is equal head, and let tortoise. It's the first thing here that we wrote down in our board there. And then okay, hair next, and we're gonna say hair is equal hair next dot next, because if we have a cycle, that will be true, and tortoise otherwise will be false and will fall into the exception or outside the loop basically. And if hair equal tortoise, we will return true. We don't need to actually prove the value here. I mean, you have a value, this value, dot value, but it will always be the actual value, because the actual extension of the list is on the dot next node, not actually here. So it will always be the actual value, but there's a value method, which is very confusing at some point. Anyways, otherwise, outside the loop, we will return false. Right? So if you try to find a cycle, if the cycle is found by being on the same next iteration, if they fall over in the same place, it will be true, otherwise it will be false. Let's see what it says here on the submission. Okay, submitted. Let's see. Okay, that's good. So that's that. Thank you very much for watching this video. I hope I shared a good reference about Floyd's algorithm with you guys. I'll post all the links in the description, and yeah, I'll keep releasing more videos about different algorithms. As you can see, I've been solving a bunch of them here recently. I just find out difficult to make time by working full-time and recording the content, and trying to catch up with all the things that are happening in the market. But yeah, I hope you guys enjoyed, and the next content, obviously I'll be covering the MIT classes with you guys, so I'll be watching those, and I'll be sharing what I feel exciting and mind-blowing from those classes, because there's a lot of good content there. Yeah, that's it. I hope you guys enjoy, and see you in a bit.